Hey, Dr. O here, and welcome to the homework solutions for Chapter 1. What you're going to find in this video is in the first several slides, I actually just show you the slide with the way that I solved the problem on it. Won't contain any narration. And so we'll go through all the problems in the chapter like that. And then following that will be a series of slides where I do provide narration and the step-by-step on how I solved the various problems. So I hope you find this beneficial. In this first problem, we're given a sample of carbon monoxide, two samples, and we're going to decompose each of them and figure out if they're the same. And in order to do that, we're going to follow the law of definite proportions. So if we read what our problem is telling us, we have two samples of carbon monoxide. They get decomposed. One sample is going to produce 17.2 grams of oxygen and 12.9 grams of carbon. And the other is going to produce 10.5 grams of oxygen and 7.88 grams of carbon. So I always like to start by writing out what it is that I'm given. So what I'm given is a sample number 1, that breaks down into 17.2 grams of oxygen and 12.9 grams of carbon dioxide. And sample number 2 gets broken down into 10.5 grams of oxygen, 7.88 grams of carbon dioxide. And we're going to figure out what the ratios are of oxygen in each one of these and our oxygen to carbon dioxide and figure out if they're the same. So how do we do that? Well, the thing that we want to do is we want to take the sample of the mass of oxygen and the mass of carbon dioxide. We're going to divide the carbon dioxide into the oxygen and use that as the basis for our ratio, because that's basically what we're looking for. So in our first example, we're going to take the oxygen and we're going to divide it by the carbon. So we're going to take 17.2 grams and divide it by 12.9 grams. And the value that we get is 1.33. Now another way that we could say that is we could write it as a ratio. And we could write it like this, 1.33 to 1. And what that's telling us is that we have 1.33 grams of oxygen for every 1 gram of carbon dioxide. Now when we run sample 2 through the same mathematical formula, we should get the same numbers. So let's try it out. So if we take 10.5 and divide it by 7.88, we in fact do get 1.33. And we could write the ratio the same way. So based upon these two calculations, we would determine that the oxygen-carbon ratios for two samples are the same and that in both cases we were dealing with carbon monoxide. Now in problem number 2, what we're going to be doing is we're going to be breaking down two different elements and we're going to comparing the mass of the hydrogen that we get from both of these. And what we're applying here is the law of multiple proportions. We're basically proving that when we combine water and oxygen and form different compounds with it, that we're still going to have a ratio that is consistent between water and oxygen across these two compounds. And the two compounds that we're going to look at are water and hydrogen peroxide. So if we look at what our problem says, we have decomposed a sample of water and we end up getting 0.125 grams of hydrogen for every 1 gram of oxygen. And if we decompose hydrogen peroxide, we're going to get 0.0625 grams of hydrogen for every 1 gram of oxygen. Now you'll notice that in both of these situations, we're comparing a variable amount of one compound to 1 gram of the other compound. So we're comparing variable amounts of hydrogen to always 1 gram of oxygen, and that's an important feature when utilizing the law of multiple proportions. One of the two compounds always has to be equal to 1 gram. So let's get started. So I always like to start by writing down what I'm given. So we're given sample 1 of water. We're going to get 0.125 grams of hydrogen for 1 gram of oxygen. And in our second sample of hydrogen peroxide, we get 0.0625 grams of hydrogen for 1 gram of oxygen. Now, how are we going to set about solving this? Well, what we're really worried about is the hydrogen, because the hydrogen is the variable component between these two ratios. So I could say then that my solution map is going to say the ratio of the mass of hydrogen from sample 1 and the ratio of the mass of hydrogen from sample 2, and I would put it in a fraction, which is basically a ratio. So let's go ahead and get started with that. Now, another way to write this ratio instead of as a fraction is to actually go ahead and use the division sign. So we can take the ratio of sample 1 and divide it by the ratio sample 2 of hydrogen in both cases. Now, why am I doing it this way? Well, I'm doing it this way because we're going to get into dividing fractions, and this is something that you learned in junior high, but a lot of people forget or didn't learn it very well. So we're going to review it here because it's going to be a skill you need throughout this term. So let's go ahead and write out what I mean by the ratio of the mass of hydrogen per sample. So in the first case, what I'm talking about is 0.125 grams of hydrogen for our 1 gram of oxygen. And we're going to write the same for our hydrogen peroxide. Now, most people don't know how to handle this, and dividing fractions is a little bit weird. It's a little bit more simple if you write it as a multiplication problem. Now, in order to do that, the thing that we need to do is we need to invert this second term, which means I'm going to put the oxygen on top and the hydrogen on the bottom and change the division sign to a multiplication sign. So let's do that. So we're going to leave the first term the same, and then we're going to multiply it by oxygen on top and hydrogen on the bottom. Now, why do we do this? Well, it's because I think most people find multiplication a little bit simpler, but the other thing that this does is it clearly lets us see that we have repeating terms. And when it comes to multiplying fractions, when you have a term on the top and the same term on the bottom of the other fraction, you can cancel those two out. So we have 1 gram of oxygen in the denominator of the first term and 1 gram of oxygen in the numerator of the second. So we can cross those out, which means we've just simplified this whole equation, and we can now rewrite this thing as a fraction, because when you multiply 0.125 grams of hydrogen over 1, that's basically what we've done, by 1 over 0.625 grams of hydrogen, then we can write it as a fraction. It ends up looking like this. Now, we still have a repeating term here. We have grams of hydrogen in the top and the bottom, so we can get rid of that, which is good because what we're looking for is just a number. We don't want any units present because we're looking for a ratio. Ratios don't have any sort of a unit. So now we're left with 0.125 over 0.0625. So if we divide 0.125 by 0.0625, we end up coming up with the whole number 2. And this is consistent with the law of multiple proportions. When we divide the mass, the ratio of mass in each sample of hydrogen, mass of hydrogen in each sample, what we end up getting is a small whole number, which is what we would expect. Now, problem number 3 gets us into dealing with isotopes, mass numbers, and atomic numbers. And this question is asking us to approach that information from 2 different facets. So let's go ahead and get started. So part A says that let's see, what is the atomic number, the mass number, and the symbol for carbon isotope with 7 neutrons? All right, so the thing that we're given here is we're given that we're dealing with carbon and that we have 7 neutrons in this sample. And we're being asked to come up with the atomic number, which we can abbreviate with the letter Z, the mass number, and come up with the symbol for the isotope. All right. So let's go ahead and solve this part first. So we're starting off with carbon, and the way that we find the atomic number is we go to the periodic table and we look for that whole number that is going to be in the square with carbon. And if you look that up, you're going to find that carbon comes in with an atomic number of 6. Now, what does the atomic number tell us? The atomic number tells us the number of protons. That's valuable information because we're going to need that in order to find the mass number, because the mass number is going to be the number of protons plus the number of neutrons. So we know the proton number is 6. We just looked at the periodic table, and we're being given the number of neutrons. So let's go ahead and set up an equation for solving the mass number. So the mass number is going to be equal to the number of protons plus the number of neutrons, which is going to be 6 protons plus 7 neutrons, and that ends up being 13. So our mass number is 13. Now the last thing that we're being asked to come up with is the isotope symbol for carbon that has 13, a mass number of 13. So the way that we do that is we take the chemical symbol for carbon, which is the capital letter C, and in the superscript on the left, we're going to write the mass number. So we're going to put 13 right there. And in the subscript on the left, we're going to put the atomic number, the number of protons, right there. And with that, we have completed A for this problem. Now, the second part of this is going to ask us to basically figure out the number of protons and then the number of neutrons based upon a given mass number, and we have to figure out what that is. So what we're given is this information about potassium. So we're dealing with an isotope of potassium. And what we need to figure out is the number of protons, which is the atomic number, and the number of neutrons. So if we're given the number, the isotope of potassium, then the thing that we can do is go to the periodic table and look up the atomic number, or we can look at the symbol right here and see that it comes in at 19. So our atomic number is going to be 19. Now, in order to figure out what the number of neutrons for this isotope is, we're going to have to use the equation that relates the mass of this isotope, making it equal to the number of protons and the number of neutrons. So if we drop in the numbers of what we know that we have a mass number of 39, we have 19 protons, and we don't know the number of neutrons. So here's our mathematical formula. 39 is equal to 19 plus some questionable number of neutrons. If we just rearrange these values a little bit, subtract 19 from both sides, we can say 39 minus 19 is going to give us the number of neutrons. And the math is pretty simple, and it ends up being that we have 20 neutrons in our isotope of potassium 39. Problem 1.4 is going to ask us to solve for the atomic mass of an element given the fact that it has 3 isotopes, and also given their natural abundance, how they occur in nature. So let's read the question. Magnesium has 3 naturally occurring isotopes with the masses of 23.99 atomic mass units, 24.99 atomic mass units, and 25.98 atomic mass units, and natural abundances of 78.99%, 10%, and 11.01%. And we are to calculate the atomic mass of magnesium. So I always like to take what I'm given and just spell all of that out. So we're going to take the information for our first isotope of magnesium, and we know that it has an atomic mass of 23.99, and it shows up at 78.99% in a natural sample of magnesium. Isotope of magnesium number 2 comes in with 24.99 atomic mass units, and it shows up about 10% of the time. And in the third version, it has an atomic mass of 25.98, and it shows up 11.01%. Now, it's always easier to eliminate the percentages and just go ahead and put those into decimals. And the way that you do that is you take your value in percent as a percentage and divide it by 100. So for our first value, 78.99%, that's going to become 0.7899. For our second value, 10%, divide it by 100, and it becomes 0.1000. And for the third one, 0.1101. Now at this point, we're ready to go. So what is it going to take? What does our solution look like with this? Well, in order to calculate the atomic mass, given the different isotopes and their natural abundances, what we have to do is we're going to take the atomic mass, multiply it by its natural abundance for each one of these different isotopes. So I have it spelled out here for all three of our naturally occurring isotopes. So let's actually plug in the numbers. So for our first version, we're going to take 23.99 atomic mass units and multiply it by 0.7899. We'll do the same thing for the second, 24.99 atomic mass units times 10, or excuse me, 0.1000. And for our third one, 25.98 atomic mass units times 0.00, I'll get it right, 0.1101. Now, if we multiply each of these out, let's go ahead and do that. We see that for our first isotope, it's going to come in at 18.9497 atomic mass units. For our second one, 2.4990 atomic mass units, and for our third and final one, 2.8603 atomic mass units. Now, you'll notice that I included 4 places to the right of the decimal in each of these answers. I basically just held on to a whole lot of decimal places, and the reason why is I'm not ready to do any rounding yet. When I'm doing the calculations, I actually want to hang on to a fair amount of those decimal places so that I can ensure that I'm getting a good version of my final number. Now we are going to round at the end, and the way that the cue that I'm going to take as far as my rounding is I'm going to look at the values that I was given up here in my original problem, and you'll notice that we have 4 significant figures in each one of these values. So my answer is also going to reflect 4 significant figures. All right, so with our 3 values here, we add these together, and we end up with 24.309 atomic mass units. And we're going to round that to 4 significant figures, which means that we're going to end up with 24.31 atomic mass units for magnesium. Now in problem 1.5, this is going to be a dimensional analysis problem, and a dimensional analysis is all about converting from one type of a unit into another type of a unit. That's really the problem, and the numbers just go along for the ride. So let's see, what are we doing here? We've got a pure silver ring that's going to contain 2.8 times 10 to the 22nd number of silver atoms, and the question is how many moles of silver atoms is that? So you might be saying, well, what are the units? Well, mole is 1 unit, and then the other unit is tucked away in here, and this unit is the number of atoms. Number of atoms. So whenever you have 2.8 times 10 to the 22nd silver atoms is going to be the number of silver atoms. That is your units. So we're converting the number of silver atoms into the number of silver moles. So you know me, I always like to start with what is given. So we are given 2.80 times 10 to the 22nd number of silver atoms, and we're going to be asked to answer the number of moles of silver that is contained in that number of atoms. So because this is a dimensional analysis, we have to figure out what two units have a standard that are going to be equal to each other. So what do I mean by that? Well, we might be saying, what is a mole equal to? How many particles of anything is in a mole? Well, we have an answer for that, and we can say that 6.02 times 10 to the 23rd number of particles, any particles, is going to be equal to 1 mole of that particle. So Avogadro's number is equal to a mole. That's basically what we have here. So what does it mean when we have this sort of relationship? Well, we could write this as a fraction, or sometimes I like to just call them a ratio, where you have one number over the other. And we could write one fraction that looks like this, where we have 6.02 times 10 to the 23rd number of particles, in this case going to be silver atoms, over 1 mole of silver. We could write it that way. Or we could say it the other way, which is that 1 mole of something, in this case silver, is over 6.02 times 10 to the 23rd number of silver atoms. Okay, so the question becomes, which one of these two ratios, which one of these two fractions do we want to choose to help us solve the problem? And the rule that I like to say is that the units you seek go on top. Well, what are we being asked to answer in? We're being asked to give our answer in moles. So we're going to choose the version of this information that's going to give us the one that has the moles on top, and that would end up being this one right there. So let's get started. So we're going to write out what we're given, which is 2.80 times 10 to the 22nd number of silver atoms. And you're noticing what I'm doing here, and this is what I strongly recommend that you do as well. So you understand what it is that what type of a unit that you're dealing with. This is not a real unit, but I'm assigning this as a unit. So at some point I can cross it out so that I know that I've set my problem up correctly. All right, so that's our given, and we're going to multiply it by our fraction, by our ratio. So it's going to end up looking like this, and we're going to multiply that. And the thing that you're noticing is that I'm also going to put this first term as a fraction as well. Any number over 1 is equal to that number, so we could write it this way. Now, why am I writing it this way? I'm writing it this way because I know a lot of students are challenged by fractions, and visually this makes it a little bit simpler to understand if something is located in the numerator or the denominator. So once we have it written like this, the thing that hopefully becomes apparent to you is that we have number of silver atoms in the numerator and in the denominator, which means now we're set up to eliminate those units. So a moment ago I said that dimensional analysis is really all about converting from one type of a unit to another, and the numbers just come along for the ride. That's exactly what we just did right here. I didn't worry about what was in the number part of either one of these. I was just concerned with what kind of units. So I know that I want to get into moles, and that I have to get out of number of silver atoms. So I created I used the fraction, the ratio, that's going to allow me to do that. So it allows me, by intentionally selecting this one, to put a unit I'm trying to get rid of in the bottom, in the denominator, so that I can cross it out in the numerator. And then the only units that I have left are going to be moles of silver, which is how I want to answer my question. So if we simplify this, we can rewrite this to say 2.8 times 10 to the 22nd moles of silver is divided by 6.02 times 10 to the 23rd. Now there's no units left in the bottom. The only units that we have are moles of silver. And when we do this math, we end up getting 0.04651 moles of silver. Now this is a perfectly fine answer. You could leave it like this, but I know in the back of the book that it's actually put it in scientific notation. And scientific notation requires that in the mantissa, the numeric part of the term, you have one number to the left of the decimal place and then two numbers to the right of the decimal place. So we can do that, and that means then that we're going to end up with 4.65 times 10 to the negative 2 moles of silver. In problem 1.6, we're being asked to take something that's been given to us in grams and convert it into moles. So our problem states, calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So with this problem, what we're only given one piece of information, which is the amount of copper, 35.8 grams of copper. And we're being asked how much is this in moles? So when we're considering what our solution might be, our solution pathway, we have to think, what is going to allow us to create a relationship between grams and moles? Because we have two different units here and we're being asked to establish a relationship between them, which mainly means getting out of one unit and into another one, and that is clearly the realm of dimensional analysis. Well, it just so happens in chemistry we have something that is called molar mass. Molar mass allows us to create a relationship between grams and moles. It tells us that so many grams of a substance will contain is contained within 1 mole of that substance. So if we go to the periodic table, we can see that copper has an atomic mass unit of 63.546. Now, why is that a big deal? Because we can just drop the atomic mass units and substitute grams per mole. So this is telling us that we have 63.546 grams of copper per 1 mole of copper. Now, whenever we have a ratio or a fraction written with two different types of units, we can write that fraction one of two ways. So one way we could write that fraction is 63.546 grams of copper over 1 mole of copper, or we could say 1 mole of copper over 63.546 grams of copper. So we have two choices now. With this information relating these two different units, we can create two different conversion factors, and we have to be able to pick the correct one. Now, the rule of thumb is that the units that we seek go on top. Well, if we go back to what we're given and what we're being asked to render an answer in moles. So the conversion factor that we're going to select is the one that has the moles on top. So let's get our problem set up, and I always like to start with what I'm given, which is the 35.8 grams of copper. And now we're going to plug in our conversion factor, which is 1 mole of copper over 63.546 grams of copper. And just to make it a little easier to read, and so we can define what is in the numerator and what is in the denominator, I'm going to put our given value over 1, just basically turn it into a fraction. Now, when we do this, we can see now that we have grams of copper in the numerator here and grams of copper in the denominator here, and we can go ahead and cross out those grams of copper. They're repeating terms top and bottom, and they go away. They're going to cancel each other out. And this leaves us with the only units of mole, which is perfect because we're being asked how many moles. So I'm going to do an intermediate step here and do some math, and I'm going to basically multiply 35.8 by 1 mole of copper, and that's going to give me 35.8 moles of copper, and multiply 1 by 63.546, and that gives me 63.546. And now at this point, all I have to do is divide 35.8 by 63.546, and my answer is 0.563 moles of copper. Now in 1.7, we're being given some information and asked to do something that we really haven't encountered before, but you're going to find it's not that big of a deal. So let's read the problem. So how many carbon atoms are there in a 1.3 carat diamond? And diamonds are a form of pure carbon arranged in a different and quite lovely pattern. And you might be saying, I don't know nothing about going from carats to atoms. Well, that's okay, because they're giving you a huge gift right here. They're telling you that 1 carat is going to be equal to 0.2 grams of carbon. That's what they're telling you with that. And that is going to be our first step in solving this problem. So, as always, I like to take what I'm given and write that down. Just go ahead and identify everything. So I know that I'm given 1.3 carat of diamond, and I'm being asked to tell how many carbon atoms that is, and I'm being given this lovely clue that 1 carat of diamond is equal to 0.2 grams of carbon. All right. Now, to this point, whenever we solved a problem, I told you that as we set about creating conversion factors, you're going to put the units that you seek on top. But in this case, we're going to be using more than one conversion factor. And whenever you're using more than one conversion factor, it's not so much that you're putting the units that you seek on top, because those intermediate steps don't get you the units that you seek. Instead, what you're doing is you're putting the units you want to eliminate on the bottom. So when you have multiple conversion factors, you're going to back into your answer. So you're going to basically look for the units you want to eliminate and make sure that those units are on the bottom in your conversion factor. Make sure they're in the denominator of your conversion factor. So with that in mind, let's set about creating a solution map. So the first piece of information we're going to use is this right here, that 1 carat of diamond is equal to 0.20 grams of carbon. And we know that when we have information that relates two different types of units, we can create two different conversion factors. And in this case, we can create one where the carats on top and the grams are on the bottom, or we can create another one with the grams on top and the carats on the bottom. Now, our given value is in carats, and we want to eliminate carats in this first step. Regardless of what units we get ultimately in this first step, we know that we need to get rid of carats. So we need to pick the conversion factor that puts the carats in the denominator, and that's going to be this conversion factor right here. All right, so now that we're out of carats, we're now left with the units of grams. Now, we're in chapter 1, we're learning how to do conversion factors. Don't make this any harder than you need to. Chances are we're going to end up using molar mass to get us out of grams and into moles. And if you think about that, we want to do that because moles will ultimately get us to the number of particles. And that's basically where we are in this particular part of the chapter, so this is what we're going to do. So now we're going to look at the molar mass of carbon. And we know that if we go to the periodic table that carbon comes in with 12.01 atomic mass units, which is the same thing as saying 12.01 grams per mole of carbon. And we can write this conversion factor either with the grams on top and the moles on bottom, or the moles on top and the grams on bottom. Now, from our previous conversion factor, we basically got out of carats and into grams. So in this second conversion factor, we want to get out of grams and into whatever is next, which in this case would be moles. So the conversion factor that we're going to pick now is going to have grams in the denominator. Grams are going to be on the bottom, which means we're picking this conversion factor right here. So with this second conversion factor, we're now in moles. And we do know something that will correlate moles and atoms. And that information is this. Avogadro's number of carbon atoms is equal to 1 mole of carbon atoms. And now we're correlating number of atoms with moles, two different units. We can create two different conversion factors. So we can put the number of atoms on top, the moles on the bottom, or the moles on top and the number of atoms on the bottom. And if we go back to our second conversion factor, that got us out of grams and into moles, but ultimately we don't want to be in moles, we want to be in number of atoms. So we're going to pick the conversion factor that gets us out of moles. Moles will be in the denominator, and just so happens leaves us with the number of carbon atoms on top, and that's going to be this conversion factor right here. So while we still have all of this on the screen, let's set up the equation. Put all the conversion factors in and start with that. So I always like to start with what I'm given, which is 1.3 carats of diamond. And our first conversion factor is going to be this one right here, 0.2 grams of carbon over 1 carat of diamond. Our second conversion factor is going to be 1 mole of carbon over 12.01 grams of carbon. And our third conversion factor is going to be 6.02 times 10 to the 23rd number of carbon atoms over 1 mole of carbon. So now let's turn this into a problem that we can solve. So just for visual purposes, to make it easy, I always like to turn this first term into a fraction, just so that we can see what's above the line and what's below the line for each term. And because we're going to be doing some multiplication, let's go ahead and drop in our multiplication signs. Now, the first thing I like to do when I've got a problem like this is I like to cross out repeating terms, which means I'm looking at crossing out units that are both in the top of a term and in the bottom of a term. So in the case of carat diamonds, we do see carat diamond on the bottom here and carat diamond on the top there, and we can cross those out. And if we look to grams of carbon, we can see it's in the bottom here and in the top over there. And if we look at moles of carbon, we can see it's in the bottom in our last term and in the top of our third term. And with that, we've eliminated all the units except for the number of carbon atoms, which is a good thing because that's how we're being asked to give our answer. All right, just to show you how much this cleaned up our problem, I'm going to rewrite each one of these terms without the units. So here's our first term, here's our second term, here's our third term, and here's our fourth term with the units. Now at this point, what you want to do is you want to multiply everything on the top, and then you want to multiply everything on the bottom. And I'm going to do that. So I'm going to multiply everything on the top and everything on the bottom, and I end up with 1.565 times 10 to the 23rd number of carbon atoms over 12.01. And now we just finish out the math, which means I'm going to divide the top by the bottom, and I end up with 1.30 times 10 to the 22nd number of carbon atoms in our 1.3 carat diamond. Now in problem 1.8, we're being given a titanium cube, and we know how many atoms it contains, and now they're asking us to figure out what is the edge of our titanium cube. So we're going to have to figure out how the volume of a cube is calculated in order to figure out that edge business. So I know it sounds like an undoable task, but trust me, it can be done. And of course, they're giving us a wonderful hint right here, telling us what the density of titanium is, because that will allow us to correlate the grams with the volume in that cube. The cubic centimeters is a volume measurement. Now I know that we've got grams here, we have atoms here, but we've already done a number of problems where we know the pathway to get out of grams and into atoms, and then this little bit right here will tell us how to get out of grams and into centimeters cubed. So I always like to start writing down what I'm given. So the thing that I'm given are the atoms of titanium. So I've got 2.86 times 10 to the 23rd atoms of titanium, which I abbreviate with the hashtag and the name of the symbol of the element. And I'm being asked to come up with the length of the cube, which I'm designating with the letter L, and we need to find out how many centimeters that it's going to be. Now, another piece of information, like I said, that's really going to be important to us is that density measurement. So we know that the density of titanium comes in at 4.5 grams per cubic centimeter, and that's going to become important to us as we solve this problem. Now let's go ahead and set about figuring out our solutions map. Now, At the beginning of this problem, I said that we need to know how the cube is calculated. And a cube is calculated based upon its length, its width, and its height. It's a volume measurement, and that's how you would take the volume of, that's how you would calculate the volume of a cube. Now, because this is a cube and not something like a rectangle or some other odd shape, the thing that we would know about a cube is that the length is equal to the width, and it's also equal to the height. So another way to write this is to say the length cube is how we're going to calculate the cube volume. So that's going to become important to us later on. Now let's set about getting out of atoms and into grams. So if we're starting off with atoms, the thing that we can say about atoms is that we know that the number of atoms is going to be equal to 1 mole. So when we have the number of atoms and correlating it with moles, we know we can develop two conversion factors, one with the number of particles on top and the moles on the bottom, or the one with the moles on the top and the number of particles or atoms on the bottom. All right, so if we get out of atoms and into moles, then we need to find a way to correlate moles with something else, maybe like grams. So we're going to take molar mass, which we know that is going to be equal to grams per mole, and in this case for titanium it ends up being 47.87 grams per mole. Now we're correlating grams and moles, which means that we can put the grams on top and the moles on bottom, or the moles on top and the grams on bottom. Now with this maneuver, this will get us out of moles. Let's see, is that what we were in? Yeah, moles, and get us into grams. But we still have that density value that we're going to use. So the density is equal also to a grams over centimeters cubed, because ultimately that's the value that we want, is a centimeter value. So with this, we know that we can put the grams on top, centimeter cubes on bottom, or just the opposite. So let's back into this like we did in the previous problem, back into this using multiple conversion factors, and we have to calculate which one that we're going to use at each step. So we're going to be starting off with a number of titanium atoms, and so we want to make sure that this value is in the bottom of our conversion factor, so it looks like we're going to be using this one right here. Now when we get out of number of titanium atoms, it's going to put us into moles. So in this second conversion factor, we want the moles of titanium to be in the denominator, and that ends up being this value, this conversion factor right there. Now once we're out of moles of titanium, we're going to be in grams of titanium, but we don't want to be in grams of titanium. We want actually to be in centimeters of titanium. So in this last conversion factor, we want the grams of titanium to be on the bottom, which means that it's going to be this conversion factor that we're going to be utilizing. So now we have our three conversion factors. Let's just get the skeleton of our problem in place. So we're going to start with what we're given, which is 2.86 times 10 to the 23rd number of titanium atoms. And we're going to take our first conversion factor and drop that in, and our second conversion factor and drop that in, and our third conversion factor and drop that in. And now we have the skeleton of our equation that we're going to utilize to solve at least part of this problem. Now, because I like to keep these things easy to read, that is knowing what number is on top, what number is on bottom, I'm going to go ahead and turn this first term into a fraction by putting it over 1. And I'm going to drop in my multiplication signs because we're multiplying all these values. And I'll know if I've set my problem up correctly once I start crossing out the units. So if I look at my first and my second numbers here, I can see that I have number of titanium atoms on the bottom here and on the top there, so that's good. If I compare my second and third values, I can see that I have moles of titanium on the bottom and the top, so those cancel out. And if I look at what I've got in my third and my fourth values, I've got grams of titanium on the bottom and grams of titanium on the top. The only units left are going to be cubic centimeters of titanium, which is perfect. That's exactly what I want. So I'm going to rewrite all of this without the units, going to leave out all the units that I crossed out. So here's my first term, and my second term, and my third term, and my fourth term, the only term that has any units left in it. Now, having done this, I noticed that I've got 10 to the 23rd here and 10 to the 23rd there. So I'm going to go ahead and cross those out too, so I don't have to use the exponent button on my calculator. Now this becomes just a simple multiplication and division problem. So I'm going to multiply 2.86 by 47.87, and then I'm going to multiply 6.02 by 4.5, and I end up with something that looks like this: 1.36.9082 centimeter cube of titanium over 27.09. And I like to hang on to all these extra decimal places because I'm not in the mood for rounding at this point. Now at this point, I'm going to divide the top value by the bottom value, and I end up with 5.05382791 centimeter cubed of titanium. Am I done? Well, I don't know. Let's take a look. So here I have centimeters cubed, but here I have centimeters. So no, I'm not done. I now need to cube this value, because remember we said that in order to get that cubic centimeters, we had to multiply length times width times height, which in this case is L times L times L. So now we're going to cube this value so that we can find the value of L, which will give us our answer. So we're going to take our value that we just came up with, and we're going to put it under the cube root sign and perform that mathematical function. And we end up with 1.716 centimeters. Not really of titanium, but of our titanium cube. Now, am I going to leave it here? I could leave it here, but if I come back and I look at the numbers in the values that they gave me, I see that I've got 3 significant figures. So I'm going to make mine have 3 significant figures too, which means my value is going to be 1.72 centimeters in my titanium cube.